Hello and welcome back to SN Tutors. Today we'll be talking about acid-base chemistry. So I'm going to go ahead and just draw a line down the middle here because really in organic chemistry you focus on two types. On the left is Lewis, acid-base. In parentheses I'll put complexation. And then Bronsted-Lowry over here on the right. I'll just abbreviate it like that. But in parentheses, I'll put proton transfer. Okay, so let's start with Lewis, because this is by far the most simple reaction in organic chemistry. So in Lewis complexation, our acid is an acceptor of electrons and our base is the donor of electrons. So let's look at boron. See, boron is odd because it's able to take on having only 6 electrons in its valence shell. So that makes it a very good Lewis acid. Another example is aluminum. It's really anything that is in the boron group in the periodic table. And then a Lewis base is literally anything with electrons. So I'll just put in like water. Water is H2O, right? It's got electrons, 2 lone pairs right there. And they're both localized, so that makes it really basic. And really all that happens is these electrons go out and grab the boron, and here's our product. And the one thing you got to keep an eye out for is formal charges. So if this was neutral and just formed one more bond, I'll draw the electrons there so you could see it, then it's going to be plus, right? So it has 1, 2, 3, 4, 5 things surrounding it when it did have 6. And since oxygen has a valence number 6, 6 minus 5 is plus 1, so it's plus. And then boron becomes minus for the same reason if you just look at the periodic table. But yeah, there's your product for the first type. Yeah, so that's basically Lewis complexation in a nutshell. Bronsted-Lowry is a proton transfer. So I'm just going to draw this out right here. So we have an acid, which is the donor of the proton, and we have a base, which is the acceptor. So if we draw the products and then draw the curved arrows, this is what happens. It goes out, grabs the hydrogen, and never forget to draw these electrons in this bond going to the acid to form the conjugate base. So the conjugate base is A minus. And the conjugate acid of the base is HB. Okay. So do you see how this is actually reversible? Which means we can calculate an equilibrium constant, KEQ. And this is where pKa comes into play. So basically, it's 10 to the power. You gotta know this equation. This is fundamental. The KEQ of this is 10 to the power of the conjugate acid's pKa, so that would be this. So I'll say pKa, I'll call this R for the right side of the reaction. And over here, I'll call this L for the left side. Here, I'll just write the L down here so you could see it better. So it's pKa of R minus the pKa of L. So in this case, R is the conjugate acid and L is just the acid. So this is extremely important in acid-base chemistry. And so when something is completely deprotonated, that's when the KEQ equals 10 to the third. So this up here has to equal 3 in order for this acid to be completely deprotonated by this base and for this reaction to occur to completion. So I hope that was helpful. Thank you for watching this episode of SN Tutors. Make sure to subscribe and let me know in the comments if you have any questions. Thanks.